Welcome back to The Explainer. So today in episode 1.3, we're jumping into a foundational concept that every power planning engineer hits on literally day one. We are looking at normalizing the whole grid using the per unit or PU system. Now, I know what you're probably thinking. Oh, great, we're going to spend the whole time doing tedious grid math. But actually, scratch that. I want you to completely reframe how you look at this. We aren't just doing math. We are looking at the ultimate translation device for a ridiculously complex electrical grid. If you want to understand how power flows or how system stability is maintained with all these new renewables coming online, you absolutely must speak the language of the grid. Let's dive right in.
Okay, let's dive into this core problem. Our electrical grids are built on multiple, vastly different voltage zones. You might see power generated at 11 kilovolts, stepped up to sub-transmission networks at 33 kilovolts, and then pushed way out to massive transmission networks operating at 132 kilovolts, 345 kilovolts, or even 765 kilovolts. Trying to compare raw amps or raw ohms across these distinctly different zones is an absolute mathematical nightmare. It's kind of like trying to compare your salary in US dollars to your monthly rent in Japanese yen. Without a common currency, those numbers mean absolutely nothing relative to one another. We desperately need one common scale to make sense of the whole system. To really illustrate the chaos of not having that common currency, just trace the path of this standard IEEE safety diagram on the screen. Look at this incredibly scattered mess of raw values. We've got an equivalent source on the left, an overhead line, a 115 to 12 kilovolt step-down transformer right in the middle, and then the load. And the numbers are all over the place. We have positive and zero sequence impedances with raw ohms, ground resistance at 2.5 ohms, and then transformer specs based on 25 MVA. If you try to manually calculate fault currents across this whole thing, bridging across that transformer while juggling raw ohms in totally different megavolt ampere bases, it is cross-zone comparison chaos. It's just impossible to do efficiently.
So enter our hero, the per-unit system. This is an absolutely brilliant method of expressing system quantities, like voltage, current, power, and impedance, as simple fractions of a defined base quantity. The formula is beautifully simple. Your per-unit value is just your actual value divided by your base value. When you apply this, that messy diagram we just looked at completely transforms into a clean network of consistent numbers that usually hover right around 1.0. An actual voltage of 115 kV in a 115 kV base zone, that becomes 1.0 PU. An actual voltage of 12 kV in a 12 kV base zone, also 1.0 PU. Suddenly, those transformers that physically step voltages up and down, the ones you'd normally have to track manually with strict turn ratios, effectively disappear from the math. The whole grid becomes one unified, continuous circuit.
Getting there is a super straightforward four-step process. First, you pick a single system power base, or MVA base. This applies to your entire grid no matter what. Second, you pick a voltage base or kV base, but this one is specific to each individual zone that's bounded by transformers. Think of those two foundational pieces, power and voltage, as your master keys. Once you define them, they unlock the rest of your base equations. In step 3, you calculate your base current. For single phase, it's just power divided by voltage. But for the three-phase grids we actually operate, you take your system power and divide it by the square root of 3 times your line voltage. And finally, in step 4, you calculate your base impedance. It's a highly logical, cascading sequence.
Let's zoom in on that final step for a second, the base impedance. The formula is Z base equals V base squared divided by S base. Once this base impedance is established for a specific voltage zone, every single physical line, machine, and fault resistance in that zone simply divides its raw ohm value by this exact base. This process powerfully strips away all those incompatible raw ohms that were causing us so much trouble earlier. What you're left with is a universal, dimensionless per-unit value that you can cleanly analyze side by side with equipment operating in a completely different voltage zone across the grid. But hold on a second. I need to pause here and issue a massive warning. If you're analyzing grid data, there is a literal monster in the woods waiting for you, and it's called the change of base trap. I'm using a serious tone here because skipping or forgetting this step wrecks more junior engineers' first power system studies than literally any other error. Here's the deal. When you get data from a manufacturer about a generator or a transformer, they provide the impedance based on their equipment's specific ratings, not your overall system's base. You absolutely cannot just blindly plug their numbers into your grid model.
Now, what's really interesting about this slide is how perfectly the IEEE source diagram illustrates this trap. Look at the transformer specification zoomed in on the right side. It says Z1 equals ZO equals 0.2 plus J10% on 25 MVA. That on 25 MVA is the manufacturer's nameplate rating. It is the equipment's old base. If you take that and plug it directly into a 100 MVA system study without converting it, you aren't just slightly off. You're introducing a catastrophic, multifold error that will completely wreck your downstream fault calculations. For example, if you skip this step and plugged a generator's 15% reactance on a 15 MVA base straight into a 100 MVA study as if it were 15%, you'd be introducing a staggering 6.7 times error.
So, the crucial point is, to avoid this disaster, you must rely on one specific equation. You've got to use this exact change of base formula to mathematically bridge that manufacturer nameplate data to your overall system base. Your new per unit impedance equals your old per unit impedance multiplied by the ratio of the new and old power bases, and then multiplied by the square of the ratio of the old and new voltage bases. This formula is your absolute best friend. It safely transports a piece of equipment from the isolated world of the manufacturer's factory floor directly into the unified ecosystem of your specific grid study.
Okay, let's do a quick quiz. I mentioned earlier that engineers typically use a standard 100 MVA system power base for their grid studies. But why 100? I mean, why does the entire industry unilaterally standardize on 100 MVA instead of just using arbitrary numbers like the 25 MVA we saw in that transformer, or maybe 37 or 50? Is there some hard physical limitation of the electric grid that forces us to use the number 100? Take a second to think about it.
Well, the answer is actually incredibly practical. There's absolutely no physical grid requirement forcing the number 100. It was chosen purely for mathematical convenience and easy mental math. Because the base is 100, dividing or multiplying by it is basically instant. It translates decimal per unit values into percentages right in your head. If you're looking at a 12 MVA transformer and your system base is 100 MVA, that transformer's capacity reads instantly as 0.12 per unit. You know at a glance it represents exactly 12% of your system's base capacity. That human convenience is the entire reason 100 MVA became the industry default.
And this brilliantly illustrates the true elegance of the per-unit system. We started off with a chaotic multi-voltage mess with raw values scattered everywhere. But by applying this system, we unified it. We've normalized all our equipment onto a common mathematical base, whether it's sitting on an 11 kV distribution feeder or a 765 kV transmission line. We identified that dreaded change of base trap, and we learned the exact formula to avoid it. Your grid is now a beautifully clean, normalized mathematical canvas, perfectly prepped for the next phase of analysis.
So your grid math is finally normalized and unified. But having this perfect, dimensionless mathematical canvas raises a pretty terrifying question. What happens when the chaotic, unpredictable physics of real-world synchronous generators and grid-forming inverters crash into this perfect math? How in the world do we build accurate internal models of these massive physical machines without breaking our pristine per-unit ecosystem? Well, that is the challenge of Phase 2 component modeling, and it changes absolutely everything. We'll be diving into that next time, but until then, thanks for watching this explainer.